limits, Unit 16. Today's Monday. And what's kind of fun about this unit, I hesitate to say it because some of you will think, oh no, that's not good. Like this, you can, if it makes you feel better, you can mark out the word pre on the notes. Like this is calculus. The questions and concepts we'll look at today and this week and next, these could easily be questions on the AP exam that the calculus students will take in a few weeks. So we have definitely jumped from pre-cal into calculus. And limits the concept of a limit is the entire backbone of calculus. I'm not even sure my calculus students realize that, because it's kind of going on in the background of all that we do in calculus. Once we learn it and use it, then we kind of stop talking about it, but it's still going on in the background. This concept opened up huge doors for great advancements to be made. Without limits, calculus would not exist. In fact, there's a little joke, a very mathy joke. There's a city in Texas, I forget which one it is, but their little motto is a city without limits. And so calculus teachers once in a while share the joke around like, haha, they're not allowed to do calculus in this city. Like, nerdy joke for calculus people only. But it's true. Like, without limits, you could not do calculus. And without calculus, that opened up all sorts of stuff. Going to the moon. Have you watched the show Hidden Figures, that movie? Any of you? There's lots of math in there. There's only a few things that they like reference by name that a calculus student might catch. But definitely lots of calculus going on in all of our technology. So pretty cool. And calculus is also a relatively recent discovery. Excuse me. Like everything up till now has been known for thousands of years. Like even a squared plus b squared equals c squared. Sines and cosines, those have been around. Maybe not sines and cosines. Those have been around a long, long time. Relatively speaking, calculus was discovered or invented, however you want to phrase it, in like the 1700s. So, that was a long time ago. But relative to adding and subtracting, this is relatively new stuff. So that's kind of fun too. All right, so what is a limit? And this is such a big deal, and it's a very different deal. It doesn't feel very mathy to some people initially, and that's kind of a hard part for it. Because math, we generally think of as like exact, right? Like 2 plus 2 equals 4, period. And that's why some of you like math as opposed to English, right? Like there's no subjective stuff about it. Go ahead, sharpen your pencil. And there's nothing subjective about limits, but it doesn't feel as concrete as 2 plus 2 equals 4. And so it takes a little while for some people to get their head around what is going on with limits. Once they do, it's really not that big a deal, especially today we're going to be looking at graphs. So it's an easy, relative to the other things, introduction to limits. Think of a limit as the intended height of a function at a certain value of x. So the question is not where do we get to, but where are we headed? Like where do we think we're going to? What's our goal? Whether we get there or not, that's a different kind of question. It's the height of a function is the y value when it's graphed. So a limit is the intended height, the intended y value of a function at a certain value of x. It's the value that the function thinks it's going to. Right? This feels weird. Like what? Why does it think it's going to? Why doesn't it just go there? Sometimes it actually goes there, sometimes it doesn't. But where does it think it's going to? It's the value that the function thinks it will attain. It might get there, it might not. We don't care. We only care about what the value is approaching. That's its limit. Okay, so this is kind of weird, and it's going to be weird, especially on this first example, because it's actually going to get there. It's maybe more helpful when you look at a graph where it doesn't get there. Like, well, where was it headed? Where did it land? We'll see that in a minute. Consider the function x cubed minus 3x squared. So graphed out for us there. The height of the function, same thing as the y value of the function, changes as x goes from left to right. And remember, you read a graph like you read a book, left to right. So we're increasing and then decreasing and then increasing. Look what happens to the height as x goes toward 1 from the left. So think 0.99999999. So we're not really at 1. We just want to get close to 1. So we're coming in this way. We're getting closer and closer and closer. We don't care about getting there. Like, limits are not getting there. Limits is what are we getting close to. Well, it sure looks like we're headed toward -2. Looks like -2 is our intended height. Coming from the left anyway. Look at what happens as x goes towards 1 from the right. 1.001. So a little bit more than 1. Or 1.01 or 1.0001. Like we're sneaking up on x equals 1, but coming from the other direction. It sure looks like y is headed toward -2. Again, it's a little bit weird because it gets there. So it's like, why are we talking about limits? Why can't we just say the function is -2 there? It's like, well, it doesn't always get there is the problem. Approaching an x value from the left or right is called a one-sided limit. And so you're kind of doing, when you're coming from the left, like you're ignoring the right side. You're only looking at what's happening from the left. And when you're coming from the right, you ignore the left. You're only worried about what's it look like coming from the right. And so maybe already you could realize that if you had a piecewise function, then left and right limits might be different. Where am I headed from the left versus where am I headed from the right? Those are different things. So piecewise is one place where we'll get confused a little bit later. Let's talk about notation and how to even say what we're looking at here. So how we say that is the limit, LIM, as x approaches 1 from the left. So x arrow 1 means x approaches 1. From the left is that little minus sign. So 1 minus. Not -1, it's a little less than 1. So that is definitely a new notation of 1 with a minus sign up there. That's weird. That's new. The limit, LIM, x approaches 1, x arrow 1, from the right, there's a little plus sign there. Okay, so what are each of these limits? As x approaches 1 from the left, that was the first one we did over here. As x gets closer and closer to 1, our y value is headed to -2. And because it's headed to -2, we will say the limit equals -2. We don't know if the function gets there or not, but the limit equals -2. We're headed towards -2. Limit as x approaches 1 from the right. So as we head towards x equals 1 from the right-hand side, our function is headed towards -2. Its intended height is -2. Now, this next sentence you're probably fine with. Thank you. If the limit from the left is equal to the limit from the right, coming from the left, coming from the right, if they're equal to each other, then we can say like this overall limit is equal to whatever that limit is. So the left limit equals the right limit, that equals the limit. Maybe that seems simple and dumb, but it's pretty important in a little bit for limits. And even the AB calculus students, as simple as that seems, at the end of calculus, we haven't talked about limits in a while, they'll mess that up sometimes. Okay, so you might be wondering why we would do this, because like, what is the point? Like the function at 1 equals -2, so who cares that we're like getting closer and closer? Okay, well that's just an intro. Limits get far more interesting, at least to calculus teachers anyway, maybe not to students. Okay, well, look at that picture. Before we look at any of the words on that picture, what's interesting, maybe that's not quite the right word for students, what's different about that graph? What do you notice right away? Yeah, there's a hole there. So something's going on here. Why does the graph have a hole at 2, -4? You know the answer to that? No, it's like sort of the limit is going to be downstream from the hole. I mean, those are very much related things. But you can answer this question without knowing limits. Yeah, the factors cancel, right? That's what makes a hole. Factors that cancel. So if we factor out x squared from the top, factor out x squared from the top, then the x minus 2's will cancel, and hopefully remember that that's a hole at x equals 2. Okay, that's pre-cal stuff. That's algebra stuff. We haven't talked about limits yet, but now we maybe algebraically know why there's a hole there. We can't plug in 2 because it makes the bottom 0. Okay, well, as x approaches 2 from the left, x approaches 2 from the left. So like I'm getting closer and closer to 2 from the left, so I'm coming in this way. What is that function headed towards? What's its intended height? Where do we think it's going to land? 4. And then as x approaches 2 from the right, the little plus sign means from the right. These are coming in on this way. What is our function headed toward? 4. Are they the same value? Yes, 4 equals 4. So that means the limit as x approaches 2 of that function is 4. It's headed toward 4. Now we don't care what the actual value of the function is at x equals 2. In fact, in this case, it doesn't even exist at x equals 2. We only care that the y value is getting close to, is being approached. It's the intended value. All right, let's talk about a piecewise function. Briefly mentioned that a minute ago. Here's our example. Let's see. Let's make sure we understand what we're looking at here before we start into the calculus stuff. Equals x squared when x is less than 2. So that would be this piece. Yeah, that's x squared, but only where x is less than 2. 7 minus x, but only when x is greater than 2. Okay, so we understand where the graph comes from, how it's related to that function. Limit as x approaches 2 from the left. So we're coming from the left. That would put us on this branch. So what is that limit? What does the limit equal? Because what is the value? What is the function approaching? 4. And then from the right, so we're at x a little bit bigger than 2, and not like a little bit bigger like 4 and 5, but like a really small bit bigger, like 2.01. We're approaching 5. And because we're approaching 5, the limit is equal to 5. I think some of that's a little bit confusing. It's like, well, do we ever get to 5? It doesn't really matter. We're approaching 5, so the limit equals 5. Well, I'd ask for the next one, but it kind of gives the answer right there. So what's the limit as x approaches 2? Read ahead one line. D and E does not exist, and we will use D and E a lot in calculus and in this section. The limit from the right doesn't equal the limit from the left. D and E doesn't work. They don't have the same limit. So we can't say, you don't average, you don't pick one. It doesn't matter that 5 there's a closed circle and at 4 there's an open circle. That doesn't matter. Like that's at 5 or at 2. We care about as we get close to 2. So one's headed to 4, one's headed to 5. Overall, nothing. D and E. Use the graph of the piecewise function to give each limit. Okay, let's do a few of these together. As x approaches 1 from the left, as x approaches 1 from the left, what do we think? Yep, headed towards 7. There's not a dot there, but we don't care. We just care that approaching 1 from the left is 7. These are sort of grouped, so we're going to do these like this. So you don't want to just like work all the way down the page here. Limit as x approaches 1 from the right. Also 7. Limit as x approaches 1. 7. Like from the left and the right is both 7, so that limit is 7. What about g of 1? Good, that's the dot, that's 2. Like the function at x equals 1, the height is 2. Even though the limits were up there at 7. Alright, why don't you try the next 4, 8, 10. Sure, where the g of 1, where did that come from? So this means the function at 1. We're not caring about limits, none of this approaching business, just if x equals 1, what does y equal? And so we go to x equals 1, and the dot is at 2. I mean, there's an open circle up at 7, but the open circle expressly means that we're not there. We're somewhere else. And there's a dot at 2, so g of 1 is 2. The function when x equals 1 is equal to 2. Even though the limit as we approach 1 is up there at 7. But that sort of is a mathematical explanation of why this graph is weird. Because there's a hole up there, the dot's down here, well, the limit's up there, the function's down there.
For a function, we're looking for a dot?
Well, you're looking for where you're only looking at the one specific value. So g of 1, it's like you're only looking at, like I can't narrow my fingers narrow enough, right? I'm not looking to the left or to the right. I only want to know where the graph is. And maybe it's a dot, maybe it's part of a line, like g of 4 is negative 2. The limit's negative 2 there as well, but g of 4 is negative 2. So function evaluation is just like that one narrow spot.
Will there ever not be a function?
Possibly. It's possible that they're not defined. Looking on this one to see if that's true here. I think, by the way, this should be g of negative 2 to make it match all the others on that little section. Let me add one to this. G of negative 5. Alright, so you try those, check with a neighbor. I'll see if I can find some popsicle sticks so that we can all... Okay, so far? Kind of getting the hang of it? Limits of infinity, limits at infinity. Consider this function, x minus 1 over 2x minus 4. Let's do a little pre-cal first, right? Like x equals 2 would be a vertical asymptote. Right, because that would make the bottom 0. And so sure enough, there's a vertical asymptote at x equals 2. Also looks like there's a horizontal asymptote there at 1/2. That's our pre-cal information. Now let's see if we can do some calculus with that. As x increases without bound, what is the height of the function approaching? So that means as x gets really, 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 really big, so not just 9 or 10, but 11 or 12, or maybe 100 or 1,000 or 1,000,000, what is the limit what is the function, what is the height of the function approaching as x gets really big? 1/2. This is still sort of graphically, but we'll get there. Where if x is a million or 100 gazillion, then the 1 and the 4 don't matter so much, right? Like if you got a million minus 1, then minus 1 is meh. So that sort of equals x over 2x, which equals 1/2. So that's sort of the more mathy way to get there rather than just looking at the picture. This is called a limit at infinity. As x goes to infinity is a limit at infinity. The limit as x goes to infinity. If a limit as x goes to infinity is a real number, like 1/2, then you have a horizontal asymptote at that value of y. So up here we could have said, so therefore we have a horizontal asymptote at y equals 1/2. So that we are supposed to know the horizontal asymptote from pre-cal already, but now we have a kind of a calculus approach to a horizontal asymptote. If a limit as x goes to negative infinity is a real number, then you have a horizontal asymptote at that value of y. So that would be on the other end. Question, can a function cross a horizontal asymptote? Here's where your math teachers have sometimes lied to you when they said you can't cross an asymptote. Like, not true. You can cross an asymptote. Let's just say yes. There's a lot more to it, but the answer is yes. You can cross a horizontal asymptote. Not a vertical asymptote, but a horizontal one is fine. All right, let's look at the next picture. Consider f of x equals x minus 2 over x minus 4. Limit as x approaches 4 from the left. Limit as x approaches 4 from the left. So 3.9, 3.99, 3.9999999. What do we think that answer is? Good, that's going to negative infinity. And here's where it's even tricky in calculus. Even the AP test is a little bit ambiguous on this. If it's negative infinity, it's officially D and E. But you could answer it either way. Negative infinity is a better answer because it's a little more precise. But that means it's not a real number, so the limit doesn't exist. How about the limit as x approaches 4 from the right? That would be a positive infinity. So the limit as x approaches 4? Definitely D and E. Yes, it's positive infinity on one side, negative on the other, D and E.
So positive is not D and E?
Sorry, positive infinity is also a D and E. If it's anything other than a number, it's D and E. I mean, it can be a weird number, 1/2 or 0.7 repeating, or who knows, but if it's anything other than a number, then it's officially D and E. So there's sort of different types of D and E. There's infinity D and E, but there was also the left-right D and E. Can a function cross a vertical asymptote? The answer is no, it cannot. So if your answer is infinity, then that means you have a vertical asymptote. If you're approaching infinity and you get an answer, that means there's a horizontal asymptote. But it's usually easier to just look at the picture to pick off your horizontal and vertical asymptotes. All right, so the next page is kind of a summary of everything we've done. Things to keep in mind when looking at a graph to evaluate a limit. Every one-sided limit exists unless the limit is infinity or negative infinity. So I don't like the way that's worded. It's like everyone exists except. Like, well, number 2, for a regular limit, meaning not one-sided, if there's a hole, the limit exists and it's the y value of the hole. Like, we didn't phrase it quite like that, but we saw that. So if there's a hole there, the hole is the limit. It doesn't matter that it's not filled in. For a regular limit, if there is a break in the graph, the limit does not exist. I would even say a jump might be a better way to phrase that. All right, so if there's a break in the graph or a jump in the graph, there's no limit there. The limit as x approaches infinity or negative infinity gives you a horizontal asymptote. Yeah, that makes sense. As x gets really big or really small, if the graph is approaching some number, then that's what a horizontal asymptote is. If the answer is infinity, then you've got a vertical asymptote. Limits of infinity, technically D and E, it's a special case of D and E. There's 3 reasons a limit doesn't exist. We've covered 2 of them. The third one's kind of tricky. We're not going to worry about that one yet. So the 2 reasons for us to have a D and E are a mismatched left and right limit, or infinity. The other one is oscillating, and that's a little more confusing. We're not really going to worry about that. But just so you don't have incomplete information. If something's oscillating, then it's not approaching anything. It keeps going back and forth. All right, piecewise function f of x is defined above, or graphed above. Some wacky graph there. Evaluate each limit if possible. If it doesn't exist, write D and E. Let's see. I don't know that we need to do all of those. So let's do however many popsicles that we have left, so that everybody gets to play today. So let's do the first 8. Then we'll move on. We'll call that good enough. So you try the first 8 of those. And if you haven't been called yet, you will be shortly. So again, there's our answers to 1 through 8. How about 15? As x approaches negative 8 from the right, what's happening to the graph? As x approaches negative 8 from the right. Positive infinity, which means does not exist. So for now, I think I just want you to put both of those things. Because the more helpful, precise answer is infinity, but technically that means it doesn't exist. So put both. If that's on a multiple choice test, both of those won't be answers because they're both right, so we wouldn't do that. On a multiple choice test, we would have one of those answers, but not both as the choices. And then how about as x approaches infinity? So this is sort of the other way. X is getting really, 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 really big. What is our function approaching? 4. So that makes that a horizontal asymptote. And the one before was a vertical asymptote. All right, today's assignment's worksheet 1. Kind of long notes.